The OSI model. It is the most referenced protocol model in the industry today, and still none of today's popular network protocols follow it directly. Today we're going to look at the OSI model and start by defining what it is. Next we're going to look at layered communication and the advantages that it offers us. We're going to look at the different layer responsibilities within the OSI model, and finally we're going to cover data encapsulation. What is the OSI model? It is an abstract reference model developed by the International Standards Organization, ISO, in the early 1980s. The reason the ISO decided to develop this model was that IBM, through SNA, was cornering the market, and they wanted to keep it competitive and keep their foot in the market, so they said let's standardize as a whole and keep everybody somewhat level. Now the OSI reference model, as it says here, is simply a guide to network protocol development. What we have is 7 layers: the application layer, the presentation, the session, transport, network, data link, and physical. Remember, in its entirety, this is simply a guide. When we take this guide and apply it to a real-world protocol like TCP/IP, we see similarities. The application, presentation, and session layers, all 3 of these are combined into what is known as the application layer. The transport layer maps directly across. The network layer does as well. And in the final 2 layers, the data link and physical layer, map to the physical layer of the TCP/IP stack. Let me take a step back and define for you what a network protocol is. I have a computer here that I'm going to label N1 for Nugget 1. I also have a distant end computer that I want to communicate with that I'll label N2. Each of these computers have a user in front of them. Let's say that these users are running a chat program. What happens is I have an application layer here that is a GUI, a front end for this person to view and to type in information and hit enter. Once I hit enter, the transport, the network, and the application layers take care of this data and get it ready to be transmitted over a physical medium, the cables that are connected to your PC, over to the other PC, where these first 3 layers are going to reconstruct the data so that it is viewed by this individual exactly as I typed it in here. And now everything I typed in here was sent across, rebuilt here for his viewing pleasure. I have included this discussion on TCP/IP and its model just to give you a reference or a big picture sense and ground you into what we're talking about when we're introducing the reference model. But keep in mind, this section covers the OSI model, so that will mean that we will discuss each layer and the responsibilities associated with each layer, even though they're not particularly applied in their entirety in the real-world scenarios like TCP/IP or the network protocol. Continuing our definition of the OSI model, we find that the OSI model also is a reference model, which we knew already, for layered communication in a networked environment. So this is what's new to us, layered communication. Let's discuss what that is. We'll start by taking a look at the first rule of layered communications, and that is each layer provides a standard output to the layer below and facilities for use to the layer above. What does that mean within our model? Let's look at the presentation layer. That means that it's going to provide a standard output to the session layer and facilities for the application layer. By facilities we mean choices or categories for the data put in at the application layer to be funneled through in the presentation layer. So that's easy when I'm talking about a layer that has a layer above it and below it. But what about the application layer? While you can see that it might have a standard output, and it does, to the presentation layer, what facilities does it offer to the above layer? That's when the user comes into play. Understand that the application layer is simply the GUI, or the graphical user interface, or the front end for this user's viewing, and it also can be the options within that program. That takes care of the top 3 layers and the fact that they are user-facing. But what about the bottom 4? We say that the bottom 4 layers, the transport, network, data link, and physical, are network-facing. In other words, their job is to prepare the input data by the application for transmission over the physical medium. The OSI model was built on layered communication because of the advantages that it brings to the table. Namely, we have 4 listed here. First of all, divides the complexity of internetworking into discrete steps. Could you imagine trying to design a network protocol and having to address the user interface, develop a data format, build acknowledgments, recovery, and routing options within it, as well as define a protocol for transmission over the physical media? That would just be too much to ask. Because it divides the complexity of internetworking into discrete steps, if you develop the user interface, everything below that as far as data formatting, acknowledgments, and routing will take care of itself, because you will just provide your user interface a standard output out of that to the next layer. Sounds much easier, doesn't it? Alright, the next one. Allow standards-based software development. A good example of this is IPsec, which is the IP security protocol that was developed. What we have is, within the IP stack, we have a funnel that looks like this. On the top of this funnel we have many applications: FTP, Telnet, TFTP, and the list goes on. Then at the transport layer we have two options, TCP or UDP. Finally, at the network layer, everything is IP. So what the IPsec protocol was able to do was standardize based on this model and say, we're going to encrypt right here at the network layer. Make all the applications come to us. Instead of having to write security encryption for each type of application here, they simply said, let the data come to us and we will write an encryption model right here in the middle of the stack. The layered model also allows specialized development of modular software. A good example of this is going to be IP, which resides at a network layer. And underneath that network layer, I have many options for data link protocols. They can be 802.3, True Ethernet, HDLC, PPP, SLIP. I mean, the list goes on. But the beauty of layered models is that each of these modular type data link protocols can plug into IP because of the understanding of the standard output of the network layer to them and the facilities that they offer the layer above. Isn't that awesome? You can kind of get an idea of why our software today is much more powerful than before they introduced the layered model of internetworking. Because before you had to develop so much more. Now you can spend more time on the bells and whistles and the actual functionality of the application without having to worry about the transport and how that data is going to get across the network. Let's look at the next bullet. Enables peer-to-peer communication on a per-level basis. To explain that, let me bring up two PCs, as we've done in the past, N1 and N2, each having 7 layers below them. The application layer is where Telnet resides. As a user on N1, I'm typing in commands. Now those commands are not executed on my local machine, and they're not executed on the wire, and they're not executed within the stack on N2. They're executed at the application layer on N2, which helps development as well to know that input here equals output here without having to address the traveling of up and down the stack. There are many more advantages to the layered communication model, but these are the most noteworthy. Alright, so far we've looked at what is the OSI model. We've also talked about layered communications and the advantages of layered communications. Next, let's look at the layered responsibilities. What that means is we have each of our layers here on the side, starting with the top, number 7, application, presentation, session, transport, network, data link, and physical. Now we're going to look at what is each layer supposed to do. First of all, application. Used for applications designed to run over a network. As we said, applications running from one computer to another, so over a network. The application layer is used for that design and that user interface. Presentation. Responsible for data conversion and formatting. At this layer, this is where you'll usually see data formats like GIF or TIFF or JPEG, those types of formats as options. The session layer establishes, maintains, and ends network sessions across a network. Again, it's important to say across a network because it's from one computer to another. An example of this is NetBIOS in their naming and their session commands. Both are examples of session type work and responsibilities. The next layer is the 4th layer, the transport layer. This layer manages flow control of data through windowing, acknowledgments, and error recovery. Now understand, this session layer sounds like flow control, and it is, but it's the flow control of the conversation, the starting and the ending of the conversation. The transport layer talks about flow control of the data, and so that's the segments of data that we're going to transmit, because these top three layers up here are user-facing, up to here, and options in the programs for users. Once we hit the transport layer, we're looking downwards and saying, how am I going to get this information to the other computer? Another responsibility of the transport layer is to divide raw data streams into segments. Understand that if we're using, let's see, a user program of FTP, and we want to transfer a file from one computer to another, this file can be very large, and we can't transmit it all at once because of the limitations on the physical media down here and the size of the packets that it can transfer. So what transport layer does is it makes sure and breaks up that bulk data into individual segments that can be addressed and transported over a physical medium. It's kind of like a scene from an Old West movie. In the town, you have a building burning here, and of course on the other end of town, you have a well. Now what you would like to do optimally is take all the water in the well, deliver it to the fire, and put it out. But realistically, you have people in this path, and they can only carry so much. Again, the limitation of the physical medium. So you have to have buckets of water right here transferred from person to person and thrown on the fire. Eventually you will get the job done. You will have this whole FTP file transferred to another machine, but you have to understand the limitations of your physical medium. The network layer has many responsibilities. The first one is responsible for end-to-end delivery of packets across the network. End-to-end delivery. What I've done here is I've included two protocols that reside at this layer just so you get an idea of what they do. IPX and IP, or what is done at this layer. So it's saying that from N1 to N2, I'm responsible for the delivery of this packet. It doesn't matter that these computers are right next to each other on the same local area network or across the world over 14 hops or 14 routers. I am still responsible for end-to-end communication at this layer. I also define the logical addressing to make that happen, because if I have a starting point and an ending point, I have to have them uniquely identified, and that's what our logical addresses will do. As in the case of IP, something you might see out there is 192.168.1.2. That's the logical addressing that we're talking about. Another function fragments packets based on the differing MTUs. We talked about the limitation of the physical medium down here. As you go from network to network, let's interject routers here. Each router connects to a network. And these physical mediums will change. If I have Ethernet here, FDDI here, SLIP here, and fast Ethernet here, each one of these can have a different maximum transmission unit. That's what an MTU is of the packet. Basically, it's just saying how large can this packet get at its max. Because these differ, you might send a packet from N1 at a size of 1500, get to the SLIP link and have an MTU of 552, which is smaller than 1500, and have to take this one packet, divide it into 3 packets or 4 packets, and send it on its way. That's called fragmentation, and that's completed at this network layer as well. And finally, convert segments to packets. What are we talking about here? Basically, we started with a bulk of data in the application or user interface. The transport layer segmented that into smaller, more manageable pieces. The other thing it did that we didn't mention there was connect a header in front of each segment. And that header helps the transport layer on N2 know what to do with this segment. You've got to remember peer-to-peer communication. So on N1, any instructions given at the transport layer will be instructions for the transport layer of N2, not any layer beneath it on N1 or beneath that transport layer on N2. So there's specific instructions in the header. The same thing for the network layer. When it has that same data segment that was at transport, complete with its header, it adds a header of its own because it has instructions for its peer on N2. Now we call this new data form a packet, and up here it was called a segment. The idea of adding specific instructions at each layer to the original data so it can be communicated to to the distant end at its peer level is called data encapsulation, and it's something we're going to cover in more detail later in this series. So let's move on to the data link. The data link defines the protocols used to transmit and receive data on the physical medium. Examples of protocols at this layer are 802.3, ATM, FDDI, and the list just goes on. Basically what we're doing here is we're framing the output that came from the network layer so that it can be physically moved over the physical medium to the distant end. Once the framing is completed, we move into the next layer that defines the physical and electrical characteristics of the transmission medium. What we're really talking about here is the connectors, the cables, the encoding, and the voltage involved at this layer. So there you have it, the 7 layers and the responsibilities at each layer. There's a lot to take in, so what I've done is I've worked up a model to represent each of the layers. First of all, we have the application layer. Again, the graphical user interface, the GUI, is mainly what we see at the application layer. I'm going to represent that here with our entry into our application. First thing we see is the GUI. We'll start by making representations of user input. These are data bytes being input on the screen by a user at the GUI. At the point that the user hits enter, this information or these data bytes have to go through the presentation layer, which is responsible for data formatting. The result of passing through the presentation layer will be data on this side of that gate that is formatted in TIFF or ASCII or JPEG, any of those types of formats that we spoke of on the whiteboard earlier. Now that our original data has been formatted correctly, these 2 boxes are going to represent information provided by the session layer for establishment, maintenance, and ending of conversations or sessions. This data will pass through this area. Next is the transport layer. First we're going to talk about segmentation of the data. We have areas designated here. 1, 2, 3, 4, 5, and 6. All the data that we have that came through the presentation layer and the session layer has to be set into specific areas for transmission later down our stack. So there's 2 options. Once I present the data, which sits here, with the information of the area that it needs to be in, how do I get it there? The transport layer has a couple of choices: connection-oriented versus connection-less. To give you an example from IP, in UDP, if the information was given to the data of what area to be in, we would just send them on their way in hopes that they get to the right area. The connection-oriented option would actually be a dedicated path. We give them the information and then we take them down a dedicated path directly to their area and ensure with acknowledgement that they are in the correct area. Keep in mind with the connection-oriented example, our connection orientation doesn't stop here in the area. You have to watch that packet, or the stack will, all the way through all the layers over the physical media to the other computer. So let me draw my data in the different areas now that it has arrived. And we're going to talk about network layer functionality. The network layer is denoted by the dotted box that we see here, right outside each of the areas. Finish drawing the data bits. So the first thing the network is going to do is packetize the data. Put it in nice, orderly format inside the network layer. And it's going to do that for each of these network layers as they're represented. And the second functionality it has is the routing. Remember when we talk about routing here, it's from end to end. It's going to do that through logical addressing and route tables on routers throughout the physical media until it gets to N2. But before we get to the physical media, we have to address the data link layer, and it talks about protocol definitions, specifically protocol definitions on how each of these network entities is going to go into our physical media. So it will define who goes first, who goes second, and the path that they take to enter this physical media. The end result will be a standard output from the data link layer to the physical layer, or the transmission media, to be sent across the network to its final destination, in this case, the other computer. So you're probably saying to yourself, I'm glad we showed this in a model. I can see the interaction between the different layers, but why this particular model? And here's your answer. What I've done is I have two airports represented here, DFW and LAX. The scenario for this model is you're dropping off a teenager at DFW Airport to take a flight to LAX and visit the grandparents. Now let's talk about the layers. First, the application layer. This area was represented by the GUI, Graphical User Interface, in our last whiteboard. Now it's the terminal area of an airport. So you can go in here. In fact, there are many people in here, but you're in here with your teenager. Once you hit enter and move to the presentation layer, or in this case, a security checkpoint, you can no longer go in. In other words, your view of your data is gone, and your teenager proceeds alone. At this presentation layer, or the security checkpoint, they make sure you have a limited number of bags. Bags are a certain size, and that nothing in your possession is prohibited by the airlines for travel. At this point, you can consider your teenager formatted, as in the data formatting that is done at the presentation layer. Next, the session layer. Your teenager is going to walk up to a booth of monitors that will talk about departure times and arrival times. That information on those screens is provided by the session, the departure, the arrival, or the end and the beginning of different conversations. Now there's a fine line to be drawn here. The session layer is going to provide the information on departure and arrival times, but the transport layer is actually responsible and represented by these monitors. And they give more information than just departure and arrival of the flight, but also the gate information that's going to represent the segmentation. And you can see our gates here. Gate 1, 2, 3, 4, 5, and 6. So as your teenager finds out what gate he needs to be at, he is going to proceed to that gate. At this point, there has to be a choice between connection-oriented or connectionless protocol. In other words, do you need help getting to your gate, whether it be a wheelchair by an attendant or the people mover by a different attendant? That would be connection-oriented. Or can you wander there on your own, under your own power? That would be connectionless. In this case, our passenger found out he has to be in gate 4. Now the transport layer is going to deliver the passenger to the network layer into this dotted line. How does that happen in an airport? First thing that happens is the cattle call. So everybody comes in and they're formed nice and neat into packets, as we spoke of on the previous whiteboard. An additional responsibility of the network layer was end-to-end communication. In other words, ensuring that this packet was routed properly to the destination. That's why we're going to include our pilot in the network layer. Data link layer responsibilities included protocol specifications so that we would be ready to go across the physical media. Here we're going to have our runway, which is the path that our packet is going to follow to get to the media, and we also have ATC, which stands for Air Traffic Controllers, that are going to give us the information of taxiing, who goes first of all these packets that are associated trying to get to LAX, and who goes last. Once our data link has prepped our plane for takeoff, we're able to enter into the physical media. The physical media here is represented by a jetway, which has to do with direction and altitude that the plane is allowed to fly through to have a unique and dedicated path to land at LAX. Excellent. Now that our packet has landed in NS2 or at LAX, you simply run up the protocol stack as we had run down over here in DFW, and our teenager is met by his grandparents. There it is. The OSI model made easy. Alright, so far we've looked at the OSI model, what it is, layered communications and its advantages, the layer responsibilities that we just covered, and the last section is going to be data encapsulation. You got a glimpse of data encapsulation in our earlier conversations on segments and packets. So let's look at it a bit more closely. I have a computer here, N1, and a computer here, N2. The 7 layers of the OSI model are represented here. We start with the data at the top layer. Now, for the OSI model, encapsulation is represented with a header at each layer. Now again, the header is information specific from this peer or this application layer to the application layer on N2. And then we just see the model. The data and the previous header are attached to another header, and that continues down the line through each of the layers up to the physical layer, because at this point we don't add anything onto the frame that we have in existence. We simply translate that into ones and zeros for transmission over the physical medium. Moving from the abstract to a real-world example, we can show the TCP/IP model here. TCP/IP model has an application layer, a transport layer, a network layer, and a physical layer. Remember, in reference to the OSI model, the TCP/IP model has an application layer that maps to the application, the presentation, and the session layers. The transport layer maps to the transport, the network layer to the network, and then the physical layer in the TCP/IP model is a combination of the data link and the physical layer of the OSI model. So let's look at our encapsulation. In this example, we're going to have computer N1 transferring data to computer N2 via FTP. Alright, the first thing we have is a chunk of data at the application layer. This chunk of data has to be segmented. The reason for segmentation is, remember that down at the physical layer we have a maximum transmission unit, and we have to start being aware of that MTU at the transport layer. So this segmentation is going to happen. A portion of the data will be placed here, and it'll have a header on it. This header is how the transport layer of one computer communicates to the transport layer of another computer. Remember, peer-to-peer communications. These are the instructions for that layer. Once we have this entity put together, it's called a segment. Then we move on down to the network layer. It has the original data, the header from the transport layer, and now a new header from the network layer. And the reason for this again is specific instructions from one layer on one computer to the same layer on another computer. After that, we move down to the physical layer. The original data, the transport header, the network header, and now a physical header, or a data link header. And that should make a frame, right? But you got to hold on. Look here, we have a trailer. This trailer has to be added, and then now it becomes a frame. Then this entity is put on the wire, the physical medium, and transmitted across. And to do that, it's converted into ones and zeros, or binary. Let me give you a mnemonic that I use to help myself remember the encapsulation process. In other words, segment, packet, frame, and then the conversion into binary. When my kids go out into the sun for an all-day session of baseball or soccer, I put a sunscreen on all of us, and usually it varies in strength, but a lot of times it'll be SPF 10. And so you can see pretty readily how this helps me to remember encapsulation. S for segment, P for packet, F for frame, and then the 10 represents the binary ones and zeros. Hopefully this will be as useful to you as it has been for me. In this nugget, we talked about the idea of the OSI model being a guideline for network protocol development. We also saw the inherent advantages of the layered communication model in the way that each layer provides a standard output to the layer below and facilities for use by the layer above. Then we went a step further and looked at the responsibilities of each layer. And we ended up with a detailed look at encapsulation, showing how the original data is transformed into a segment, then a packet, then a frame, and eventually binary form to go over the physical media. I hope this has been informative for you, and I'd like to thank you for viewing.